Hello, I am Dr. Deepthi and we are studying different concepts in maths under the heading Decreations Mathematics. The broad area we are concerned with is that of linear algebra, and in that the focus is on matrices. In today's episode, we are going to talk about orthogonal matrix. If you recall, we have been talking about different types of matrices since past few episodes, and the type of matrix that we are going to look at in this episode is orthogonal matrix. Now, it is assumed that you're well versed with all the topics we have studied so far under the title Decreations Mathematics. So, I want to share with you that foundation for this particular episode on orthogonal matrix is the episodes which are concerned with what a matrix is, then matrix multiplication, transpose of a matrix, and types of matrices. So in types of matrices, we had episodes about row matrix, column matrix, square matrix, in which specific cases were that of identity matrix, scalar matrix, and in the recent episodes we have talked about symmetric matrix where the condition was A transpose is equal to A itself. Similarly, we had talked about skew symmetric matrix where the condition was A transpose is equal to negative of A. Now we are going to talk about one more type of real matrix. When I say real matrix, all the elements are real valued, and that is orthogonal matrix. And what is the condition here? The condition is that A transpose is equal to its inverse. Now when you see this condition, if A transpose is equal to its inverse, if I multiply it by A, what should I get? It should be equivalent to A into A inverse, so it should give me the identity matrix back. So let us try to verify this condition. Given an orthogonal matrix, this is the orthogonal matrix, and 1 by 7 is the scalar taken out, and inside you have elements, namely 3, 2, 6, minus 6, 3, 2, 2, 6, minus 3. So we are going to multiply this original matrix with its transpose. Now I hope all of you remember that transpose is basically exchange of rows and columns. So this row 326 becomes column here 326. So let's start the multiplication. The scalars need to be taken outside, 1 upon 7 into 1 upon 7, which will basically give you 1 upon 49. Now row 1 and column 1. So 3 into 3 plus 2 into 2 plus 6 into 6. You can see it here. So 3 into 3 is 9 plus 4 13 plus 36 49. So 49 into 1 by 49, that gives you 1. So I have shown you this first part. I would suggest that you pause the video and calculate rest of the elements, and only when you finish it resume this video. So here you can see if I take row 1 and column 2, it will be 3 into minus 6, which is minus 18, plus 6 plus 12. So minus 18 plus 18 gives you 0. Similarly, row 1 and column 3 is 3 into 2 is 6 plus 12 minus 18, that is 0. Then row 2 column 1 minus 18 plus 6 plus 12, that is 0. Then row 2 and column 2, 36 plus 9 plus 4 is 49 into 1 upon 49, that gives you 1. Then row 2 and column 3, minus 12 plus 18 minus 6, that gives you 0. Row 3 and column 1, 6 plus 12, 18 minus 18 is 0. Row 3 into column 2, which is minus 12 plus 18 minus 6, which is again 0. And lastly, row 3 into column 3, which is 4 plus 9 plus 36, which is 49, into 1 by 49, which is 1. So indeed, we have verified that for an orthogonal matrix, this is valid. Or we can say it the other way. Since this matrix is following the condition that A transpose is equal to A inverse, it is an orthogonal matrix. Now you must be wondering, what is this word or this term orthogonal doing here? Let us try to understand it. Basically, if you look at an orthogonal matrix carefully, you will realize that all the rows form an orthonormal set and all the columns form an orthonormal set. What do I mean by that? That means if you take, let me talk first about columns because everything is going to be true for rows. So if you take pairwise, say two columns, and take their product, you will realize that it comes out to be 0. That means they are orthogonal to each other. Remember, we have learnt about it, and we know that the condition of orthogonality of say two vectors, for example u and v, is that u dot v is equal to 0. So if this is a1, this is a2, a1 dot a2 will be 0. Similarly, if you take dot product of the column with itself, that means if this is a1, a1 dot a1 should also give you 1. Let us try to check it. So here let us take the product of a1 and a2. So 3 into 2 is 6, minus 18 plus 12. So minus 18 plus 18 is 0. So this is indeed true. You can also check it for these two columns. 12 plus 6 minus 18, again 0. What about this column and this column? 18 minus 18, that is also 0. So this is also true. What about the rows? These two rows. So minus 18 plus 6 plus 12, which is 0. These two rows, row 2 and 3, minus 12 plus 18 minus 6, again 0. What about row 1 and row 3? 3 into 6 is 6 plus 12, 18 minus 18, 0. That means this condition is true. Similarly, you can check for the dot product of the column with itself. So 3 into 3 is 9, minus 6 into 6, which is 36, plus 2 into 2, which is 4, and this will be 1 by 7 into 1 by 7 because both of them have that scalar with them. So the answer is again 1. So you can verify it for all. So this is where from the term orthogonal comes out. If you want to see this in detail, you would realize that if there are two matrices, one is A and second is its transpose. So if you see this matrix A1, A2, A3, its transpose is just going to be this matrix where all the rows are becoming columns. Can you see that? Yes. So if you take their product, and we know that for an orthogonal matrix, A transpose is equal to A inverse. So A into A inverse is going to give you identity matrix. You can expand it and see that if you are multiplying, for example, row 1 and column 1. So A1 square plus A2 square plus A3 square, which is 1. Because this is the term it is leading to. Similarly, if you check row 1 and column 2, A1 B1 plus A2 B2 plus A3 B3 is 0. In this manner, I will suggest that you pause the video and verify for all of them it's going to be true. So I have already given you the answer here, that this tells you that for each one of them, so if you see for example the row A1, A2, A3, you can see that this condition which we verified some time back, that the dot product should give you 1, is true. Similarly, if you see these two rows containing A1, A2, A3 and B1, B2, B3 respectively, their dot product is also giving you 0, which was again the condition of orthogonality. So this is the idea. Also, one thing I would like to mention that 2 by 2 orthogonal matrix is of the form cos theta sin theta cos theta, or cos theta sin theta minus cos theta. In fact, you will be able to verify it. All right. So what is the take back of this particular orthogonal matrix episode? That it is a square matrix and the condition should be that its transpose should be equal to its inverse, and the condition of rows forming an orthonormal set and columns forming an orthonormal set should also be verified. Thank you.